Let's take a look at 1764 Part C, followed by 1786 Part C. The reason I'm doing this is because both use the same equation and both just do different things with the results from that equation. In 1764, they want to know the standard change in Gibbs free energy for the equation, in which case they're going to use the equation Gibbs free energy equals a negative Fn E naught. And in 1786, they want to know the value of the equilibrium constant. There, they're going to use the equation where the standard cell potential equals the negative of 0.0592 divided by n times the log of k to solve for k. In both of these scenarios, the first thing we need to do is find that cell potential. So that's the reason I'm combining these two problems, in addition to saving me some time. So let's write our half reactions, and this is where a lot of people find the problem a little bit difficult. Boils down to that balancing that we did last semester. We've got dichromate ion going to chromium, 3+, and then we have iron, 2+, going to iron, 3+. I'm going to go ahead and do the irons because all you really need to do to balance there is add an electron. So finding that standard cell potential in your charts is really as easy as falling off a log. Because it is an oxidation, not a reduction, we've got 0.775 there. And negative. Now for our dichromate, remember that's going to look a little bit odd in the aqueous environment. We're going to balance, so we're going to need two chromates, two chromiums on each side. Then we've got to add a ton of water to balance out those oxygens. I actually have to wind up adding 7 waters to balance out all those oxygens, which means I then have to come over here and add 14 hydrogens. That means I need a slew of electrons when it comes to balancing my charges, because on this side I've got 14 from my positive 14 from my hydrogens, -2 from my ion there. So I've got a total of 12 positive for this side of my equation. Over here, I have a total of 6 positive, 3 from there, 2 from there. So to balance out my charges and bring positive 12 down to positive 6, I am going to have to add 6 electrons. Whoops. That was like way off there, wasn't it? I'm going to have to add 6 electrons. So I need to balance this out to get 6 electrons on my bottom. The reason that 6 electron is so important is n is your number of electrons that you're moving. So n is 6 here, and that's where that 6 comes from. Just to be clear and emphasize that, because I think that's where people are getting it wrong, who asked me about this problem, is that equation. Let me blow it up a little bit bigger here. And a little bit neater. What did I just do? Darn it, I hit a marker instead of eraser. All right. Okay. Okay. What in the world? We are experiencing a great deal of technical difficulties. Okay, finally. 14 hydrogen plus dichromate. And I'm assuming everybody understands how we got to this point. This was just standard balancing. It's the number of electrons that usually throws people. We've got to get our charges to balance, right? I have 14 hydrogens. So these 14 hydrogens give me 14 positive charges. I have a 2 here that's negative. So I've got 14 positive plus a negative 2. That equals a 12 positive. So my net oxidation number on this side of my equation is positive 12. I have 2 chromium over here, each with a positive 3. So on this side of the equation, I have a net of positive 6. I add electrons to bring my higher number down to my lower. So I have to wind up adding 6 electrons. And that's where that 6 comes in. And that's the value that I use for n. So n is going to be equal to 6. Let me go back now and finish up. I never finished calculating my cell potential there. Go to my chart, find my dichromate reduction potential, and I find it has a value of E equals, oh, now I've lost it on the chart. Wonderful. Parts, 1.36. So I add those together. And for my cell, I find that I have a standard cell potential of 0.59 volts. So now, for both of my 2 equations, I have an E value, 0.59 volts, and I have an N value of 6. So now it's just really plug and chug. So let's go to 1764, part C. Delta G equals negative number of electrons, so I've got 6, times Faraday's constant, which you'll remember is 9.65 times 10 to the 4th coulombs per mole, which is the charge on a mole of electrons, times your standard cell potential, 0.59 volts, and that gives you a value of a negative 3,401,610 joules. That's your calculator lie. Now, the thing that they're probably asking you for is I didn't check. They always want this in kilojoules, right? Gibbs free energy is always in kilojoules, so you have to do your mathematical magic. Also, this is where your book gets really super sloppy with sig figs. We've got 2 sig figs there. So really, you shouldn't be having more than 2, but your book wants you to report it to 3. So we wind up with our Gibbs free energy equal to, go to kilojoules, negative 342 kilojoules. Next cutesy step, we're going to do is 1786. 1786, 1786 part C. Here, we've got 0.59, again, the voltage from our problem, equal to a negative 0.0592 divided by 0.597, right? When you add those two to get numbers, and even I deleted that too, darn it. That's where that 0.59 comes from, adding those two numbers together. So we've got a 0.59 volts, our standard cell potential is equal to our number of electrons, 6 times the log of K. We're needing to solve for K, so we need to isolate K. So 6 multiply both sides by that. 0.597 volts now equals the log of K. So let's give ourselves a little bit of a number here. 6 divided by 0.0592 times here's where they're being big jerks in this problem. They're having fun with math again, and they want you to make a rounding error, quite frankly, and realize that 0.59 divided by 0.59, let me clear it out, 0.59 divided by 0.059, they're saying is 10, right? Which would leave you a negative 6 times 10, or a negative 60. So they're saying negative 60 equals the log of K. They are going old school. This is the sort of stuff that we did routinely back when I was in college, before people really began using calculators all the time. And then they're saying you raise both sides by 10 to get rid of the log. So you have K equals a negative 60. And that's where they're getting it. The problem with that is everybody uses calculators. If you use your calculator for this, you get 1.6 times 10 to the negative 60, which is actually a better answer. But your book in Mastering Chemistry will take this. So what I would do is, my first attempt, I'd punch that in. If it balks at you on that, then just go ahead and punch that in. So they're having a little bit of fun with you on the algebra on that one.